Alright, let's do problem number 5. A long straight wire carrying a 5 amp current of electrons is perpendicular to a uniform B field of magnitude 10 to the negative 4 teslas towards the top of the page as shown in the sketch. Find the magnitude and direction of the total B field at points P, Q, R, and S, which lie on a circle with radius 1 centimeter around the wire. So I could draw the diagram exactly how it is shown in the book, but I'm actually going to draw the diagram at a slight angle so it's easier to picture. So instead of the wire going horizontally across the page, I have it going, at an angle like this. Alright, that's just the wire. And then the B field that it's going to create is going to be like this. The B field that this wire creates is as so. And since it is shown in the diagram that the current flows like this, not only that, this is supposed to be negative current because it's a stream of electrons. So you have to use your left hand to figure out the direction of this B field. And it was like, okay, the B field is curling that way. So you can point your B field arrows like this. Those are the B field created by the wire. And then we have this thing called the innate B field, or the B field that was already there. It's the B field that points directly to the top of the page that is not created by the wire, but it's already there. So I'm going to use blue to signify that. And since it's at an angle, I will adjust the innate B field to be so. I'll call this the B innate. Okay, that's our diagram. So important thing to note before we move on is that the innate B field is 10 to the negative 4 teslas. And to find the B field of that wire, all you need to do is use this equation. B equals mu naught I over 2 pi R. You get mu naught from your equation sheet, and that's 4 pi times 10 to the negative 7 multiplied by 5 amps as given in the problem. And then the units for the mu naught are going to be Tesla times meters divided by amps. So I'm just going to put that here just for old time's sake. 2 pi, and then the radius given in the problem is 0.01 meters. You punch this in your calculator and you will get 1 times 10 to the negative 4 Tesla, and you find out that the B field due to the wire is exactly the same as the B field that is already there. Okay, now we can finally answer the question. What is the B field at point P right here? In order to find what the B field is at that instant right there, we need to recognize that, if we are traveling along this B field line, if we stop at P, the B field at that instant is a tangent line to that circle, right? At that very instant P. So you have to draw a line like this, because this is the instant at P that the B field points towards to, right? So I say the B field to the wire at P. Well, if you got your B field due, okay, so if the B field due to the wire at point P is pointing here, and the B field by, the innate B field that's already there is pointing up, then isn't the resultant B field going to be at a 45-degree angle, especially because they're both the same magnitude as well? Well, how would you picture that? Let's go over here. These two blue pens and that pencil represent the B field that's already there, and it's pointing towards the top of the page, and this is the plane of the page, and this is the wire, and the current flows like this. And since it's a stream of electrons, you use your left hand and you figure out, okay, the B field is actually flowing like this. And it might not be as obvious at first, but point P is not, I'll give you a different perspective. Point P is not up here. Point P is actually here. This is P, and this is R, this is Q, and S is actually at the bottom, okay? S is actually at the bottom here. So let's just focus on point P for now. The B field is currently flowing like this, right? And so you stop at point P, boom, right here. And then as you stop the circle here, you draw a tangent line up, right? Which is what we did on our paper. This is the tangent line to that B field. And watch that blue pen there. That blue pen is the innate B field. And don't you see how it forms a 45-degree angle out the plane of the page? Let me see if I can stick it right here. This is the innate B field. This is the tangent B field created at point P. Then the resultant B field must be 45 degrees out of the plane of the page and it's 45 degrees because they're also exactly the same magnitude. That's how that works. So now that we know that it is 45 degrees out of the plane of the page, and to signify that on our diagram, we can just do this. We can do tip to tail, this is the tip, the B field created at point P, the tangent line, and that's the innate B field. Well, the resultant has to be 45 degrees. And since they're both 10 to the negative 4 Teslas, this is 10 to the negative 4 Teslas, this is 10 to the negative 4 Teslas, and you can use special right triangles, and since that's 45 degrees, the resultant B field has to be, so I say B resultant at P equals root 2 times 10 to the negative 4. You didn't have to do any math, that's just a special right triangle, that hypotenuse there, and then out of page. Well, more accurately, like the book writes it, out of the plane of the page, and you can imagine that plane of the page to be my agenda book. And that's point P. Okay, now we need to figure out the B field at point Q. So that would be point Q in this diagram. But on the actual demonstration, we'll go over it once more. That's your innate B field. This is that wire, and the B field flows like this. Well, point Q would be right on top. And so if I'm flowing like this and I stop right here, the tangent line of that B field will be pointing here. But since the innate B field is also pointing there, you can see that the angle is just 180, and sine 180 is 0. So we know that the B field at point Q is 0 because it's a 180-degree angle. So you can say B field resultant at Q is 0 because beta is 180. Okay, now we gotta solve for point R, which is right here in my diagram. But let's turn back to the demonstration to figure out what we're actually looking at here. Okay, so again, that's the wire B field. The B field is flowing like so. Point P was here, so then we drew our tangent line up, but point R is gonna be right here. So our tangent B field line is going to point down. And you see how the B field, innate B field is here. The tangent line at point R, due to the B field created by the wire, is pointing down. Well, can't you see that the resultant B field is going to be at a 45-degree angle, but like into the page, right? You can see it. And if you were really anal about it, like, you could do like tip to tail vectors, but you know what I'm trying to say. If the B field created by the wire at point R, and you draw a tangent to it right down, that's the innate B field, well then the resultant B field is going to be 45 degrees from the plane inward from the plane of the page as is described by the book. And the magnitude of that is going to be exactly the same as that, because Again, they're both 10 to the negative 4 Teslas, and we're working with 45 degrees again. So we'll just copy what we have at 4 point P. All right, now we need to solve for point S, which is right here, which will be like behind that wire right there on my diagram. And for the last time, we'll turn to the demonstration to figure this one out. So B field's flowing like this. Point P was here, point Q was here. No, point P was here, point R was here, point Q was here. So point S must be below here. So if we're flowing like this, and we stop at point S, if we draw a tangent line here, we find that, okay, the innate B field and the B field due to the wire are just adding together, and they're both going towards the top of the page. And so that's all there really is to point S. You just add the B field. So you can say the B resultant at S is simply 2 times 1 times 10 to the negative 4 Teslas, and out of the towards the top of the page. And that's it to problem number 5. This is how you do it.